graph ranking and the cost of Sybil defense. So, how do search engines work? Well, we have a query, we have the web, and then we find the relevant pages from the web with the query. How this happens is endlessly fascinating, but we won't be discussing it today. Instead, we'll be looking at how you find the top results from the relevant pages. How most search engines work is they have a thing called rank. Every page has a rank, and it's a function of the web graph, not the query. And this ranking function is a secret sauce that differentiates one search engine from another. There's economic incentive in having high rank, because that means you're higher on the results. And where you have economic incentive, you have bad actors. In this case, spammers who want high rank and will modify the web graph to trick the ranking algorithm into giving them high rank. So our contribution is 1. We formalize the game between the web ranker and the spammer. We define 2 critical criteria, spam resistance and distortion. We show that there is a ranking function with high resistance and low distortion, which is the version of PageRank actually used by Google. And we prove lots of ancillary results about the algebra of PageRank. We're going to be using PageRank as a running example. So where did PageRank come from, and how does it work? Well, Brin and Page had an insight that good pages are pointed to by other good pages. So how do you make that usable? Well, they shopped around and eventually they settled on computing the stationary distribution of a random walk on the web graph. So what does that mean specifically? Well, you start at an arbitrary node, you take a random outage, and you go forever. The fraction of the time at each node is the stationary distribution. So what are the pros and cons of using the stationary distribution? Well, it rewards having in edges from high quality pages, and it's easy to compute. But on the other hand, it's not defined for all graphs, only ergodic graphs. And specifically, it's not defined for the web graph. So what does a grad student do when their idea doesn't work? They come up with a workaround. That brings us to PageRank, which is the workaround that saved the stationary distribution idea. It is a stationary distribution of a slightly different random walk, where with probability epsilon, you jump to a random node according to the reset vector, which is a distribution over the nodes, and with probability 1 minus epsilon, you take a random outage the same as with a random walk. And now in the original PageRank paper, the reset vector was a uniform distribution over the nodes. PageRank is defined for every graph unless epsilon equals 0. And there are 2 types of PageRanks that we'll be talking about today. When the reset vector is uniform, it's called uniform PageRank. And when it's 1 at one node and 0 everywhere else, it's called personalized PageRank. So with that in mind, let's move on to talking about the spamming game. Now, what can the ranker and the spammer do? The ranker can select a ranking function within reason. The spammer can create new nodes for free, acquire previously existing nodes at a cost, and change out edges from nodes that it owns for free. Now the ranker can combat the spammer acquiring nodes with spam detection efforts, which, along with the markets for buying websites, determine the page costs. And what the ranker is trying to do is minimize the sum of the rank of nodes owned by the spammer, whereas the spammer is trying to maximize that value. So now that we know the rules of the game, let's analyze a couple of situations. If the ranker is using uniform page rank, what should the spammer do? Well, they can make lots of new nodes for free, and thus PageRank will reset to the new nodes quite often, letting the spammer acquire as much rank as they want with no expenditure. And so therefore the total captured rank approaches 1, or 100%. And this trivial vulnerability of UPR is why it was never used at Google. Now let's talk about personalized PageRank. So if the ranker is using PPR, then what should the spammer do? As before, the spammer can make a lot of new nodes for free, but they must also acquire a high rank node that they can divert the random walks from to its own nodes, where they last about 1/epsilon steps before they reset. If you do the math, you can prove that the total captured rank is the rank of D over epsilon. Taking all this into consideration, what is a good definition of spam resistance? Well, we use the following definition. A ranking function is sigma spam resistant if, for every graph, the cost of the spammer acquiring nodes over the sum of the rank of all nodes owned by the spammer, minimized for the spammer choices, and maximized for the choice of cost function, is greater than or equal to sigma. You can show that UPR is zero spam resistant by this definition, and we prove that PPR with reset probability epsilon is epsilon spam resistant. And we conjecture that this is the best that any PageRank can do over all choices of reset vectors. With that in mind, why don't we just use PPR? Earlier, we said that the ranking function had to be within reason, and we can show that PPR is not a reasonable ranking function. We can see that nodes just downstream of C get very high rank, which is a problem because that unfairly distorts the final rankings and final positions of search results. With this in mind, how do we rigorously define distortion? Well, following Brin and Page, on ergodic graphs, we should use a stationary distribution as the reference rank. And therefore, we can define distortion as a maximum multiplicative error versus the reference rank. Therefore, we can say that UPR has poor spam resistance and poor distortion, and PPR has good spam resistance and poor distortion, which is progress, but we still have to deal with distortion. So what does a grad student do when their idea doesn't work? They come up with a workaround. So, what is the workaround? We compute two PPRs, one with center C and one with center D. We take the normalized component-wise min, which means that at any point, we take the value as the value using the PPR centered around C, and the minimum of that with the PPR centered around D. Therefore, the PPR of C will kill the PPR around D, and vice versa. Effectively, the two PPRs are grading each other's work. And now for the main theorems. For almost all choices of centers, min PPR has low distortion, almost all meaning from a sensible distribution, which we describe in the paper. Also, min PPR with K centers is epsilon over K spam resistant. So if K is small, then min PPR is almost as spam resistant as PPR. And the proof gives a natural, concrete cost function. This cost function tells rankers where to spend their spam detection efforts. One final interesting point. When is a ranking a page rank? If we fix epsilon, then we can invert the process and take a ranking P the graph and get out a reset vector. And if the reset vector has no negative values, then P is a PageRank. With that in mind, here's a fun fact about PageRank and component-wise min. If we take the component-wise min of two PageRanks, PR and PS, then we get P star. Then, if we reverse the process, we get R star from P star. And we prove that R star is non-negative for all zero, which means that P star is a PageRank in non-trivial cases. Therefore, PageRank vectors are closed under component-wise min. In conclusion, we formalize WebRanker spammer interactions as a game. We observe that all ranking functions in the literature have poor distortion or poor spam resistance, or both, and we prove that the heuristic used by Google has good resistance and good distortion. And we use the closure property of PageRank extensively in our proofs. As for further questions, there is some more work to be done on the web ranking spamming game. For example, formalize how the cost function is set. Spamming is also very ubiquitous, so can we analyze games for Wikipedia spamming, citation spamming, H-index spamming, etc.? Finally, Goodhart's law. When a measure becomes a target, it ceases to be a good measure, unless you can prove spam resistance.